Hello, this is Dr. Hanaa Assil, and today we're doing chapter 2 of International AS Chemistry at Edexcel, and this is talking about intermolecular forces. Now, what is really meant by intermolecular forces? Remember that each molecule has bonds inside it. That's not what we're talking about. The molecules have interactions between each other. That's what we need to talk about when we're talking about intermolecular forces. So basically, we're looking at molecules standing next to each other. How do they interact with each other? Remember that this is very important because if the intermolecular forces are strong, that means they will need a lot of energy to break the molecules away from each other, and that means it will need high melting point or high boiling point. On the other hand, if the intermolecular forces are weak, then only a small amount of energy will be needed to separate them or break the bonds, and that means that these molecules will have low melting point or boiling point. So let's look at the different factors that determine whether the intermolecular forces are strong or weak. First of all, if we look at the state of the substance, is it a solid or a liquid or a gas? Remember, when we were talking about solids, liquids, and gases, we said a solid, its particles are closely packed. That means they are touching each other or right next to each other. And that means that the forces between them must be strong. So solids have stronger intermolecular forces than a liquid, because we said the liquid, the particles are only slightly near to each other. Now gases, we said the particles are very far apart. This means that the forces between them, or the attraction forces between them, are actually weak. So gases have weaker intermolecular forces or attraction forces between the molecules than liquids, than solids. Then we can look at what we call giant molecules. So an example of a giant molecule is the ionic compounds. We know that ionic compounds, for example, sodium chloride, they have strong electrostatic attraction forces between positive and negative ions. Remember, we said that ionic compounds, if we're talking about its structure, they are giant three-dimensional structures with alternating positive and negative ions. So these oppositely charged ions have very strong electrostatic attraction forces between them. That means for something like sodium chloride to melt, I need to separate all these ions from each other. The interactions are strong, so I need a lot of energy to break them apart. So the ionic compounds have high melting point. So remember, if we're explaining why ionic compounds have high melting point, this is because they have strong electrostatic attraction forces between the positive and negative ions in the giant three-dimensional structure. So more energy is needed to break them apart, so the melting point is high. So what about metals? Remember, we said also metals are actually giant three-dimensional structure with regular rows of positive ions surrounded by a sea of delocalized electrons. That was how we explained the structure of metals. Now, that means that there are strong electrostatic attraction forces between the positive ions and the negative delocalized electrons. This needs a lot of energy to be broken, so metals have high melting point. Remember that the more the delocalized electrons per atom, the stronger the attraction forces. So for example, aluminium has three outermost electrons, or three valence electrons. Magnesium will have two per atom. Sodium has one electron in its outermost shell. The more the number of delocalized electrons, the stronger the attraction forces between the positive ions and the negative electrons, and the higher the melting point. So aluminium will have a higher melting point than magnesium, than sodium. Okay, we talked about diamond and graphite. And remember that we said also diamond and graphite are giant three-dimensional structures. Here they have strong covalent bonds between the carbon atoms. And this means that each covalent bond needs to be broken in order for this molecules or these elements to melt. Now, that needs a lot of energy, and that means that these giant covalent molecules have high melting. But then we look at the simple molecular structures. Now, the simple molecular structures, we said before, in general, will have lower melting point than a giant. So the giant structures like ionic compounds, metals, the diamond, graphite, silicon dioxide, all of these we said are giant, they have high melting point. But if something is a simple molecular structure, well, first of all, they will have lower melting point than anything that is giant. But what would make a difference between different molecules? The easiest, or actually the weakest, uh, intermolecular forces between any simple molecular structure is what we call London dispersion forces, or they can be referred to also as instantaneous induced dipole, or van der Waals forces. So let's see what these are. First of all, these are intermolecular forces between non-polar molecules. So in this case, we're talking about something that is non-polar. For example, chlorine molecule, we said, is non-polar. Each chlorine atom is electronegative, but when we have both of them the same, that means they're attracting the bonding electrons equally. So this we say is a non-polar molecule. So non-polar molecules are molecules that have no electronegative elements, or they have the same electronegative elements. So either way, they overall do not have any polarity. Now, if I bring a chlorine molecule next to another chlorine molecule, remember, we're not talking about the covalent bond inside the chlorine. That has nothing to do with what we're talking about. We're talking about interaction between one chlorine molecule, one Cl2, and another Cl2. Each of these have an electron cloud around. So the electron cloud around all of these, we said electrons are negatively charged. Now, if I bring another molecule next to it that also has an electron cloud, now the electron cloud of one will repel the electron cloud of the other. So they will start developing what we call dipoles. Remember that a dipole means a slightly negative or a slightly positive, and we draw that using that sign that we call delta. So each molecule originally did not have any positive or negative. It just had an electron cloud around. But then when I bring another one next to it that has an electron cloud, now that repels the electron cloud of the first one. So each of them start to have a slightly positive end and a slightly negative end. Now, this kind of attraction between the slightly negative end of one and the slightly positive end of the other, this is what we call London dispersion forces or van der Waals forces. These are the weakest kind of intermolecular forces. So these kinds of compounds that are nonpolar and the only interactions between them is the London dispersion forces, these will have low melting. So remember that the London dispersion forces are caused by the attraction forces between the slightly positive end of one and the slightly negative end of the other. How do we compare something like fluorine, chlorine, bromine, iodine? All of them are nonpolar. All of them have only London dispersion forces between them. So what determines the difference in melting point is the size of the electron cloud. So the bigger the element, the more electrons. So it has bigger electron cloud around it. So that means it will have larger induced dipoles and stronger London dispersion forces. So remember that something like iodine would have a higher melting point than a smaller molecule like fluorine or bromine. The other kind of interaction is between polar molecules. What if I have a polar molecule? So this is carbon monoxide, CO, with a triple bond between it. Alone, the molecule already has a slightly negative and slightly positive because oxygen is more electronegative than carbon. When I bring one of these next to another one, then the dipoles of one will be attracted to the dipoles of the other. So the slightly negative end of one will be attracted to the slightly positive end of the other. Now, these kinds of interactions are stronger than what we originally mentioned. They are called permanent dipole interactions, and these are slightly stronger than the weak London dispersion forces. And that means that these kinds of compounds, which are what? Which are polar, so they originally had dipoles, and then when you bring them next to each other, there is an attraction between the positive, the slightly positive end of one and the slightly negative end of the other. So this would be the permanent dipole interaction. Now, another kind of this is hydrogen bonds. Actually, hydrogen bonds are a type of permanent dipole, but these involve hydrogen. Now, hydrogen bonds will form between molecules that have what? That have an electronegative element attached to hydrogen. That's what we need. So if it has an electronegative element attached to hydrogen, that means, first of all, it originally had its own dipoles. Hydrogen slightly positive and the electronegative element slightly negative. Now, that will cause this hydrogen, which has a slightly positive charge, to be attracted to the electronegative element of the next molecule. And that is called a hydrogen bond. Remember that a hydrogen bond is stronger than a permanent dipole alone, and these are stronger than the London dispersion forces. So again, we said, when do we have hydrogen bonds? If I have an electronegative element attached to hydrogen. So water, for example, has hydrogen bonds between its molecules. Things like HCl would have hydrogen bonds between its molecules. Things like ethanol. Ethanol also has a hydrogen attached to oxygen, or alcohols in general will have a hydrogen bond. Notice, how do we draw the hydrogen bond? We draw it between the hydrogen of one and the oxygen of the other, so that the bond angle around the hydrogen is 180. They are all in a straight line. The electronegative one of one molecule and its hydrogen and the electronegative element of the next molecule must all be on a straight line with a bond angle of 180. So remember that the presence of these kinds of intermolecular forces determines which one is more higher boiling point or higher melting point than another molecule. So let us say we're comparing, for example, ethanol and ethane. Which one will have higher boiling point? Well, let's take a look. What is the difference between ethanol molecules and ethane molecules? Remember that ethanol is something that has an oxygen attached to hydrogen, so it has a hydrogen attached to an electronegative element, so it will form hydrogen bonds between its molecules. What about ethane? Ethane is just a covalent compound. It does not have any electronegative elements next to the hydrogen. It is not polar, so it will not have any interactions between its molecules except the London dispersion. And the London dispersion is a weak force. So the ethanol will have higher boiling point than ethane. Why? Because it has a hydrogen attached to an electronegative element, and that means it will form hydrogen bonds between its molecules, and these need more energy to be broken. While the ethane is not polar, It does not have an electronegative atom attached to its hydrogen, so it cannot form hydrogen bonds. So the only interactions between the molecules are the weak van der Waals forces or London dispersion forces that need less energy to be broken. So the melting point or boiling point of ethane is lower than that of ethane. Are we following how to explain these questions? Okay, what about water? Water is a covalent compound, and usually covalent compounds have low melting point and boiling point. Water is regarded as having a relatively high boiling point compared to other covalent compounds. Now, why is that? Because water, we said, has hydrogen attached to oxygen. So it has hydrogen bonds between its molecules. Remember that all of these molecules also have London dispersion forces, which are weak. This is a polar molecule, so it will also have permanent dipole, plus it can form hydrogen bonds, which are the strongest of these three. So this needs more energy to break the molecules away from each other. Remember that each molecule of water forms two hydrogen bonds. So this will have a higher boiling point than another molecule that forms hydrogen bonds, one per molecule. So remember that the number of hydrogen bonds per molecule will also determine how high the boiling point is. So water will have a higher boiling point than something like ethanol, for example. Okay, now another effect of having hydrogen bonds is the fact that the density of ice is lower than that of water. We said that solids should have higher, stronger interactions between its molecules than liquids. Liquids should have higher or stronger interactions between its molecules than a gas. This applies to all substances in general except ice and water. So solids should have higher density than liquids because the molecules should be closer to each other in solids, and that means they will have higher density, except for ice. Ice, when the water molecules start to come nearer to each other to form a solid, they are prevented from coming nearer to each other because the hydrogen bonds hold them away. So ice has this kind of structure in which the particles or the molecules cannot come any closer. They cannot form regular rows of atoms or molecules like any normal solid. So density of ice is lower than water. Of course, this is very important in everyday life because when we have a lake, for example, and the water starts to freeze and form ice, what happens is the ice is actually less dense than the water and the ice starts to float on top of the water. This prevents the rest of the lake down under the ice from freezing, and that maintains the life of the marine animals. And that's why marine animals can live inside an ocean or inside a lake while it has a layer of ice on top, because this, once some of the water has frozen, it goes to the surface, floats on the surface, preventing the rest of the water from freezing. So remember that the density of ice is lower than water because of the hydrogen bonds, and these hydrogen bonds keep the molecules from coming any closer to each other. Another effect of these intermolecular forces also, when we were talking in organic chemistry in unit 1, we said the alkanes. If I talk about the boiling points of alkanes, which alkanes have higher boiling point? We said if I am comparing the number of carbons, then the one that has more carbons will have higher boiling point. So a longer chain of carbons would have a higher boiling point. Now, why is that? You should realize that as the molecule becomes larger, then it will have more electron cloud. As we said, it has a higher electron cloud around it, and that means there will be stronger London dispersion forces between these molecules. Remember that alkanes are not polar, so they don't have any permanent dipoles. The only interactions between the molecules is the London dispersion forces or the weak van der Waals forces between the molecules. The more the number of atoms in the molecule, then the higher the number of electrons in the molecule. We have a stronger electron cloud or a bigger electron cloud. That means we will have stronger London dispersion forces between the molecules, which will need more energy to be broken. Also, we said when we were talking about alkanes, we said that something that is branched will have a lower boiling point than something that is a straight chain. So the straight chain has higher boiling point than a branch. Again, why is that? Remember, the only interactions between any of these is London dispersion. London dispersion depends on the interaction between the electron clouds. So what if I have the same number of carbons and the same number of hydrogens, but the only thing is one of them is a long chain and the other is branched? Well, you should realize that the long chain, the straight chain, can be packed more tightly. The molecules can come nearer to each other more, so there will be greater intermolecular forces between them, and that means it will need higher temperature to be broken. While the branch chain, actually, there is a limit to how near they can come to each other, so there will be less intermolecular forces between them, and they will need less heat or less energy to be broken. So that means if we're talking about alkanes, we said more number of carbons is higher boiling point. And then which one has higher boiling point, the straight chain or the branched? We said the straight chain will have higher boiling point. All of these are explained by the strength of the London dispersion forces between the molecules. More number of carbons will have more London dispersion forces, or stronger London dispersion forces, so more heat is needed to break the molecules away. And compared also to the branched, we said the long chain can come nearer to each other more than the branch, so there is more interaction between the molecules, stronger London dispersion forces, more heat is needed to separate them, so the straight chain will have higher boiling point or melting point compared to a branched chain. So remember that if we have a simple molecular structure, the weakest forces between any two molecules would be the London dispersion forces. These are weaker than the dipole-dipole, permanent dipole interaction if the molecule is polar. And these will be weaker than the hydrogen bonds, which are formed if the molecule is polar and it has electronegative elements bonded to hydrogen. And all of these will have weaker intermolecular forces, lower melting point than any of the giant structures. Remember that the ionic compounds have very strong interactions between the positive and negative ions. The covalent molecules like diamond, graphite, and silicon dioxide will have strong covalent bonds in the giant molecule that need to be broken. And all of this will have less melting point than a metal that has strong interactions between its positive atoms and the delocalized electrons. Also, the intermolecular forces will determine the solubilities of the compounds. When we were talking about ionic compounds, we said an ionic compound will dissolve in water or in polar solvents. Now, why does it dissolve in water? Because when we have the positive and negative ions, sodium chloride, for example, the negative ions and the positive ions will be what we call solvated. They will be separated because the water molecules will be attracted to each of them. Remember that water has a slightly positive end in the hydrogens and a slightly negative end in the oxygen. So the chloride ion or the negative ion will be surrounded by the positive end of the molecule of water. The positive ion, or the Na plus, for example, will be surrounded by the negative end of the water. So the fact that the water has a positive end and a negative end allows it to separate the positive and negative ions, so ionic compounds dissolve in water. What if it is not ionic? Now, if it can form hydrogen bond with water, then it will dissolve in water. So things like ethanol, we say ethanol dissolves in water. Now, why does it dissolve in water? Because it can form hydrogen bonds with the water. Now, what if it is not? It cannot form hydrogen bonds. Now, if it cannot form hydrogen bonds with water, that means it will not dissolve in water. And that is why we said organic compounds or covalent compounds do not dissolve in water. Now, that means we will need another kind of solvent, which we call organic or non-aqueous solvents. So, what kind of solvents can we use? Well, that depends on what I'm trying to dissolve. So, a solvent will dissolve something that has similar intermolecular forces. So if I'm trying to dissolve something that is polar, it will dissolve in a polar solvent. So usually, for example, acetone is a polar solvent. It will dissolve compounds that are polar. But if the compound is non-polar, then we can use something that is also non-polar, like benzene. So benzene is a non-polar solvent. It will dissolve non-polar compounds. So compounds are dissolved in solvents that have similar intermolecular forces. Thank you for listening. This was an relatively easy chapter, and please listen to the questions and answers that will follow. Thank you.